So let's imagine that you live in a big house in sunny Israel. One day, you decide you want to join the green trend, reduce the burning of fossil fuels, and make some money. You want to install solar panels on your roof. You look for a company that will install the panels, but you can't find ones that convert more than 20% of the energy reaching from the sun to electricity. You pay for the most expensive panels, you keep them clean every day, but still, most of the energy goes to waste. So what can we do to improve the solar panels' efficiency? The solution we offer is to find materials that can be used as the basis for better solar cells. The mechanisms behind the solar cell operations depend on materials that were found to fit this usage. Getting a deep knowledge of material properties allows you to tailor them best to their application, and this is also true for many other uses. The material you use should fit its usage, and there's no such thing as the best material. For example, diamond is the hardest material in nature, but you probably won't rub it on your baby's skin, and you probably won't use talc in a wedding ring. In material science, we learn about what happens inside materials around us. There are different particles building the matter, and in our group, we are interested in the interactions between them, and especially how do these change over time. We focus on solid materials, which are used for electronic and optical applications, like in LEDs, lasers, solar panels, and computer components, which we all have even in our cell phones. So there are two main ways to study materials: experiment and theory. The first one is just doing an experiment, where you make your material. It's not just, but you do an experiment. You make your material, you measure it using various experimental techniques, and then you analyze the readings you get, trying to understand the origin of your results. In these experiments, what you measure is the real material or device which will be used, which is a very good thing, but they tend to be expensive and take a long time. They can also be hard to reproduce, and sometimes you won't know if A or B caused the change that you just observed. The less common method, but way cooler if you ask me, is using theoretical calculations, which is what we do in our group. So we simulate materials and their properties using nothing but large computers. These simulations tend to be cheap and fast. They are reproducible, and you also generate all the data leading to your final result yourself, so you can analyze it back and understand the origin of your results. You can also predict the properties of materials that don't even exist yet, kind of like a unicorn. The downside of these methods is that sometimes you need to assume that the material is perfect, that it doesn't have any flaws, which is not the case in real life. So let's go back to the solar panels we discussed. To understand how they work, we ask questions about the interactions of matter with light. For example, we want to know how much light is absorbed in the material, which can also tell us about its color. The energy conversion processes involve electrons, one of the particles that build atoms. These are negatively charged particles that play a key role in chemical processes. We want to know, for example, how much light is absorbed in this diamond, and how do the electrons in this diamond interact with the bulb emitted from this bulb. So when we shine a light on the material, an electron, like this yellow friend here, can move from its initial energy level to a level of higher energy. We call this process an excitation. The different colors we see with our eyes differ one from another by their energy. For example, green light has lower energy than purple light. So if we shine the material with green light, the electron will move up to the middle energy level. But if we shine it with higher energy purple light, the electron will move all the way up to the highest energy level we see here. But the story doesn't end here. What happens after the electron is excited? Let's see together. So now let's imagine that the happy electron we saw before is a person who is leaving his house. In the physical world, this would be an electron that absorbed the pulse of energy and moved to a higher energy level. The person's absence is creating a vacancy in the house he left behind. And similarly in the material, we create a new particle called a hole. And this hole is created basically from the absence of the electron that was excited. So now we have this pink hole particle. This new pink particle, the hole, it has the opposite charge compared to the electron. So it has a positive charge. As the person enjoys his vacation, he also misses the place and memories he left behind. And similarly, in the material, the negatively charged electron and the positively charged hole are attracted because particles with opposite charges attract. And in some materials, this attraction creates a new particle called an exciton from the word excited. These excitons are basically made from the pairing of the electron and the hole. Until the person returns home, he may change, his feelings can change, the house could change. And the same thing is also true for the bound exciton. It changes over time. And this is the main focus of our study. After a short period of time, the person will return home and refill the vacancy left behind. In physical terms, this would be when the excited electron returns to its initial energy level, refills the hole, and the exciton will fade. During this process, light will be emitted, this time, for example, corresponding to yellow color. So now, let's see how an exciton looks like when we try to calculate how it spreads inside a material. So without getting deep into the details, this is what an exciton looks like inside a material. We can see silicon here. The brown lines show the atoms, and we can see places where the exciton density is high in blue and red. So going back to the story of the traveling person, each person's journey will be different and will depend on many parameters, and so is the journey of the exciton. We use computations to follow it and track the excitons from the moment they are created to the moment the electron returns to its initial energy level, refills the hole, and the exciton fades. In other words, light is absorbed in the material, and after a very short period of time, light is emitted from the material. We want to know what happens between light absorption and emission. What we do every day in the office has three major components. We first check the current state of calculations available in open source codes which are developed in universities around the world. On top of these, we then develop equations that describe the physical process that we're currently interested in. In the second step, we write some code that solves these equations, trying to be as efficient as possible, since these equations are usually very complex and demand huge computational power, storage, and memory. In the last step, we run the open source code as well as our home-written codes on large supercomputers and gather the results, which we then analyze. So I mentioned earlier two main methods to study materials, experiment and theory. We do only the theoretical part, but as I said, many times the calculations are oversimplified. To get a complete picture, we often compare our results with experiments done by our colleagues who make and measure similar systems to those we calculate. We compare experiment to theory and try to understand what is similar between the two, what is different, and the most interesting part is understanding why. And let me give you an example for that. As we said, in our calculations, the materials are usually perfect. So they are flat, they don't have any bends, they don't have any defects, they're not placed on anything else. But in practice, in the lab, or any kind of device, the materials always have some defects, they are bent, they're usually placed on some piece of glass. So these differences can be insignificant, but they can be also very significant sometimes. So now we also incorporate these defects in our calculations, trying to calculate even more complex systems, more realistic systems, and pushing the supercomputers we use to their limits. So to summarize, when we learn about light-matter interactions, we learn better about materials. And now we can even predict the properties of materials that don't even exist. So now you can properly imagine the unicorn. Thank you very much.